Hello! If you're watching this, then I'm clearly not in class. So, fortunately, I've pre-recorded a couple of lectures on special topics that are very pertinent to what we've been doing in post-production. Let's start off with signal routing and synthesis. So what is synthesis and how does signal routing apply to it? Well, let's start with some basic definitions. There are differences between synthesis and other types of virtual instruments. For example, sampling is focused on playing back stored audio using MIDI on a sampler. It's commonly used in films as a way to substitute for instruments or an orchestra in mock-up before taking it to a real orchestra. Additionally, you can use LFOs and round-robin sampling to make things more realistic by adding in vibrato or changing the sample sound every time a note is re-triggered. Synthesis, however, is creating a sound from scratch according to an algorithm or patch. Basically, it's creating a sound from a recipe. It can recreate traditional sounds to a certain extent, but it's usually used for creating new timbres and for experimenting and playing around with cross-modulation. Analog synths require hardware, but fortunately in the virtual world, analog modeling does not. And this is what we're going to look at today, analog modeling synthesis. Similar to classic modular synthesis, it's based on a modular approach. Every single unit has a specific function. Multiple modules are strung together to form a patch or program. At its most basic, a synthesizer is taking input from an input device, most commonly a MIDI keyboard, although you can use others, electronic wind instruments, pad controllers, even taking a microphone and using that to do envelope following. But it takes this input to an oscillator in the forms of a volts per octave signal and sends a gate signal that tells the synthesizer to open the envelope and sustain as long as a key is being held, and then when you release the key, it goes to a low state, telling it to close the envelope. The waveform from the oscillator is then passed to a filter, and the sound is shaped to remove any unwanted sounds. The filter output is then passed to an amplifier to further boost the signal before being sent to the final outputs. At this stage, you can also insert any number of effects. Things like reverb and delay are very, very traditional, but you can also do things like freezing, bit crushing, playing around with different types of ping pong delay, or using a chorus or flanger. Here is a very, very basic synthesis patch. This was constructed in VCV, and in fact, this was the default patch for VCV 1.6 up through 1.9. Here's a slightly larger, more advanced one. This is the default patch from VCV 2 and on. So before we get into what all these modules are, let's talk about some of the abbreviations. You'll hear me say things about voltage control, or VC, VCO, VCA, VCF. That just means voltage control, which is commonly used in analog synthesis and analog modeling synthesis. What this means is that the module is receiving voltage, pure electricity, at its input source. Electricity is controlling it, which means that any changes you make are nearly instantaneous. It can output control voltage as well, or it can output audio, depending on the type of the module. Some modules, like filters, will take in audio and use control voltage to modulate it. LF stands for low frequency and is commonly used to describe modules that operate below the range of human hearing, so generally below 33 Hertz. This is almost always going to occur in the form of an LFO, or low-frequency oscillator, which is commonly used for modulation purposes. AD, AR, and ADSR refer to types of envelopes generated by an envelope generator. AD is attack and decay, AR is attack and release, and the two can be somewhat interchangeable depending on the manufacturer. ADSR, however, is the classic. This is attack, decay, sustain, and release. And this is the sustaining model that you know and love from using all sorts of virtual plugins in Logic and Pro Tools and Ableton. Then again, CV is control voltage. Once again, this is the electrical signal running from one module to another via patch cords that tells the synth what to play. Let's look at these in a little bit more detail. So be aware that cable colors are randomized in VCV Rack. They do not correspond to the type of signal that the cord is carrying. This is pretty analogous to actual Eurorack or analog synthesis, where any number of cables will come in any number of different colors, even though they're the same length and are carrying the exact same voltage. But we do need to know some of the types that you will see on the modules themselves, typically on the in and the out port of the module. Volts per octave, or V/oct, or V/O, or even VO, is what controls pitch. For every 1 volt that you increase, you go up 1 octave. And it divides those equally into the semitones or even into microtones. Gate signals are generating a pulse similar to a square wave. When you hit a key on the keyboard, it goes high and triggers, and then it sustains until you release the key, and then it immediately dies away. This is very useful for envelopes or for sustained controls that have to stay open, like any type of routing matrix or anything similar to that. Triggers and retriggers are similar to one-shot samples. It's like a gate signal that immediately dies after triggering with no sustain. These are typically used for one-shot related devices or for clock sources so that you can sync things up to a master timekeeper. Clock signals are repeated trigger pulses that occur at a set interval and are used to control the timing of a sequencer, to sync up multiple oscillators, or for any type of repeating events. They can be used in place of a gate or trigger signal to control time sequences, or they can be used to glitch signals. They're a lot of fun. Finally, CC signals are CV signals that are mapped to MIDI control change values. We'll look at them shortly. They are insanely useful for mapping parameters out onto a physical device. A couple more conventions before we dive into this. All modules in VCV can be reset to their initial state by right-clicking and selecting Initialize. If you are playing around with this, that will be very, very useful. They can also all be randomized from the right-click menu as well. Under the View menu in VCV Rack, there is a very useful Lock Modules option that prevents accidentally dragging a module when you meant to drag a cable. I use this frequently. Cables are also infinitely stackable in VCV Rack, unlike in an actual analog synthesis environment where you would need a multiplier device. You can just hold down Control or Command and click on the output jack to stack a cable on top of an existing one and send it to multiple sources. Finally, MIDI to CV has the ability to switch to polyphonic mode, but not all modules in VCV Rack are polyphonic. So we're going to stick with monophonic for now until we decide if we want to go any further down this road. But that said, let's look at the parts of the synthesizer. These are going to be primarily the standard modules that come with VCV Rack. Starting with the MIDI to CV converter. This takes the input from a MIDI controller, although you can also use your computer's QWERTY keyboard or a gamepad, and outputs this information as CV signals to control additional modules. If you click on the text lines that currently say no driver and no device in this picture, you can change the options for driver, device, and channel. The outputs coming out where it says from device are volts per octave, which will be generally pitch, gate, which is the sustaining trigger signal that's going to go to an envelope generator. Vel will be velocity coming from the MIDI device. Aft is aftertouch, but very few MIDI devices have those built in. PW is the pitch bend wheel. MW is the modulation wheel. Then there are a number of clock functions, start, stop, and continue, that are pretty rare to find on a lot of MIDI devices. But there is a very useful one here. RETR, formerly RTRG, is retrigger, which is useful to reset the sync of VCOs or ADSR envelopes when you're playing fast and are playing a lot of quick notes. What they do is they reset the gate signal immediately. The VCO, or voltage-controlled oscillator, is the main source for creating pitch and timbre in a synth. By default, it's going to output some basic waveforms of sine, triangle, sawtooth, and square, or pulse width modulation. These are fixed waveforms. They are digital repetitions of a single waveform at different rate in wavetable synthesis. The controls that we have here are volts per octave for the inputs, sync, which is going to reset the phase of the waveform to 0 when triggered, FM, which is frequency modulation and can be scaled using the FM-CV attenuator right above it, and PWM, which is controlling the offset of the pulse width, again with a CV attenuator above it. So the pulse width controls the duty cycle of the square wave. You can make it more on or more off, depending on how you set that. Next, we have the other main source of timbre, the noise module. And just as you would anticipate, it outputs various types of noise signals. From the top down, you have white noise, which is pure randomness. It is every frequency occurring simultaneously. We tend to hear this as being slightly more biased towards the higher frequencies just because of how the human ear functions. Pink noise applies an equal power curve across the octaves, so we tend to hear this as being slightly more bass biased. Red noise is pink noise with a steeper roll-off, so it will be even more bassy. Blue noise is the inversion of this, where the power increases by 3 decibels per octave, resulting in a higher frequency bias. Violet noise is power increasing by a 6 dB per octave bias, so it will be even more treble heavy. Then we have gray noise, where random noise is subjected to a psychoacoustic equal loudness curve. And finally, black noise, which in the case of this module is gray noise with a slight bias towards the higher register. All of these are very commonly used to create things like percussion sounds, and also as a source of randomness in programs. Following that, we have the VCF, or voltage-controlled filter. The filter shapes the sound by removing frequencies from the input signal. It outputs either LPF, low-pass filter, or HPF, high-pass filter. For the controls, the frequency cutoff knob controls the cutoff frequency and can be fine-tuned with the knobs. You can use res for the resolution or the Q of the filter, and drive, which controls the amplification of the filter. The CV knobs below will continue to attenuate either the cutoff frequency, the resonance, or the drive, giving you really nice fine controls on that. Now, many other filters exist, especially in VCV rack. So if you are playing around with this at home, I do recommend downloading it and downloading a lot of the free modules. You will see quite a few other types of filters. State variable filters, finite infinite impulse response filters, many other types. The VCA is a voltage-controlled amplifier. Basically, it takes a signal and boosts it according to the level setting, which is diagrammed here with a strip of LEDs. It then outputs the results. So it requires an envelope signal from an envelope generator to open, sustain, and close the amplifier to its maximum level. It will take any valid envelope signal, but you can also change how it responds by right-clicking on it to change it from a linear response to exponential. Exponential response is closer to how humans hear and to how instruments work in terms of volume, and is a staple of West Coast style synthesis. But if you're using it to amplify, say, a control voltage signal, you might want to use linear response instead. Of course, some people don't like to use the VCA and prefer to use a mixer. This allows you to mix 4 signals together and then output either the individual channels from channel 1 through 4 or the actual mix. The level of the mix is the global output volume for the mix, and you can send a CV signal to that to open and close it, or each individual fader, 1 through 4, can control the volume of that specific channel, and they each have their own CV input for any envelope signal. So you can have individual CV values controlling level of channel 1, level of channel 2, channel 3, channel 4, or one global CV signal controlling the output volume of the entire mix. So let's talk about the envelope generator. The most common type is the ADSR, which generates an attack, decay, sustain, and release envelope when the module receives a gate signal, and it sustains it at the sustain phase until the gate signal drops low, and then it goes into the release phase. Retrigger is also really useful. It will restart the envelope instantly. Again, very, very useful if you are playing fast passages. The output is the envelope signal and it can be used however you want. It can be used to modulate the voltage-controlled amplifier. It can be used to change the frequency of a note. There's a lot of possibilities. The attack controls the time to ramp up to the max volume when a gate signal is received and goes high. Decay controls how long it takes to ramp to the sustain level from that maximum volume. Sustain is a percentage of the max volume that the envelope stays at until it's released, and then the release controls how long it takes for the sound to die when the gate goes closed or low. Again, all of these have CV inputs and attenuators, so you can dial in settings that are modulated from some other device. Of course, we have to talk about a couple of effects, in particular, delay, as it's kind of an essential effect for fattening a signal that you're playing, especially if it's in stereo. It does exactly what it says. It delays a signal. You send a signal into the input, and then you can adjust the delay time, the amount of feedback, the tone or color, which shapes the color of the delay through internal filtering, and then the dry and wet mix. Again, all of these have individual CV inputs and attenuators so that you can dial this in. You can also send a clock signal in now, which allows it to sync to a master clock so that you have, say, 16th note delay or 8th note delay. But we're not going to get into that too much. But once you've got a sound, you need to get it out somehow, and that's what the audio device is for. This is a basic 2-channel audio interface that connects with your sound interface. You change the drive, output device, sample rate, and block size using the device line above the meters. Just click on that and it comes up with a drop-down menu. Level is a master volume control that goes very similar to the other devices from negative infinity to plus 6 dB. In the ins and outs, the white bordered ports send audio to your selected audio interface and driver. So they go out of VCV and to your speakers. Black bordered ports receive audio from your selected driver. So that means they go into VCV for signal processing, using them with effects or mixing with synth sounds. This is a great way to get a microphone input so you can do a little bit of envelope following. Of course, sometimes 2 channels is not enough, and that's why they have the Audio 8 and the Audio 16, which are more advanced audio input and outputs. Basically, you use the to device section to send signals from VCV rack to that specific output from your audio interface. You can change the drive, the output device, sample rate, and block size on the respective lines. It's not just a single drop-down menu, though. Similar to audio, you have a from device set of ports at the bottom as well that will take audio in from a microphone or an instrument and send them into VCV rack for processing or mixing with the synth. You also have a recorder, which is just an audio recorder and is essential for recording your performance in VCV so you can use that performance in other programs. Basically, you connect copies of your main left and right channels to the L mon if it's mono, and to the right if you have left and right stereo. You can play a bit and use the knob to set your levels, and then, if you are ready, if you click the large button, it opens a save file dialog. Just give it a name and format, including the .wav or .aif, to start the recording at the same sample rate as your Audio 8 or audio device. If you send a signal to gate, it will record only as long as the gate is open. So this can be really, really useful if you're recording just small snippets of sound and have, say, a MIDI foot controller hooked up. If you send a signal to the trig input, it will trigger recording to start, and sending a second signal to trig will stop recording. This can be very useful if you have a key on your MIDI keyboard that you're not going to use any other time, like a really low C, or maybe there's a pad that you have and you can use it to send that. Scope is another really useful tool. It's an oscilloscope that provides a visual of the waveform that's received in the X and Y inputs. The X and Y scale or offset controls the overall scale of the waveform displayed, and the X and Y position controls the location of where it is displayed. Time controls the length of time being displayed in each frame, and you've got other options of 1x2, which will control the display mode of wave or phase. Finally, trig controls the internal rate of triggering. Just leave it alone. So, let's take a look at how we can patch all of these modules together and route signals similar to how we've been working in Pro Tools to get some cool sounds, because that's what all this comes down to. This is going to be very similar to a busing exercise, just also a lot crazier at times. So I've got some diagrams here that I want you to take a look at, and I'll explain them, and then we'll build the patches. One thing to be aware of is that these are standardized. So the cable colors in the diagram, gray is always going to be volts per octave, yellow will be audio, red is trigger or gate, blue is CV modulation, some sort of modulation source, and green is a clock function. But remember, in VCV rack, your cable colors are randomized. Let's look at a basic patch. At its most basic, this is what's going on. You have a keyboard controller sending volts per octave to an oscillator up here. Then the gate signal goes into an envelope generator. The oscillator passes audio to a filter, which is modulated by the envelope generator. The filter sends audio to a mixer, which is also modulated by the envelope generator to control the volume. The mixer sends and receives audio to a generic effects chain here, but we'll play with it with delay, which can be added at your discretion, and then the final output comes from the mixer to the speakers. Let's see it in action. So here is a basic VCV session. I have MIDI to CV already controlled and set up, and audio over here is also already patched and ready to go. So let me just connect my outputs of scope. That way we'll be able to see it. And let's start creating. I'm going to create a VCO and connect volts per octave to that. I will then create a VCF. I'm going to send the output of my VCO to VCF. I think I'm going to use the square wave here, although it really doesn't matter. You can see that the signal is going hot and it's sending stuff out already. If I click on my keyboard, we're not going to hear anything, but it is changing things. Next, I need to have an envelope generator. So I'm going to click down here and select the ADSR. I need the gate, so I'm going to take the gate from MIDI to CV and connect it here. Then I'm going to send the gate envelope out to the cutoff frequency of the VCF. I'm just grabbing random values here. Finally, I need a mixer. So I'm going to click on there. I'm going to grab... I don't see a mixer, so I will do the full values. There it is, my mixer. And I'm going to get the delay as well. There you are. So I'm going to send the low pass frequency from the VCF to input 1. I'm going to send the output of channel 1 to the input of delay. Then I'm going to take the wet out from that and send it to the VCA mix. Now I need to control the overall level of the mix. So I'm going to hold down Control, click on the envelope output of the ADSR, and connect that up to there. At this point, I can now take the output of mix and connect it up like so. And if everything works, we should be able to hear some sound when I hit a couple of keys on the keyboard. Okay, it works. It's pretty basic, but we can play with that. We can adjust the time, the amount of feedback. That might be a bit much. We'll take that down. But very basic. Just a very, very easy setup. Let's look at what we can do that would be a little bit more interesting than that. This is a bass patch. And this is the simplest of simple patches. Essentially, it is identical to the basic patch we just created, but without an effects chain. So with the bass patch, remember that you don't need to change the frequency of an oscillator if you're playing a keyboard. We just have to go to a lower octave. So I'm going to disconnect my delay. I'm going to change to a sine wave, and I'm going to drop down a couple octaves on the keyboard. And that sounds pretty good. I might want to make it a little bit more plucky though, so I'm going to decrease the attack, increase the sustain, and take the release down. Then I'm going to connect the retrigger. And that gives me a pluckier bass sound. Moving on from that, let's create a lead. In this lead patch, I am using two specific oscillators. These are sawtooths, but really anything more complex than a sine wave will work. They receive the same volts per octave signal from the keyboard, but then to make them more interesting, I'm going to detune them using the frequency controls, or I can use fine controls in the form of cents. So frequency would be large scale in the order of hertz, fine would be smaller. The two oscillators are both sent to a mixer, which controls output to a filter. So I'm going to have to swap the filter and the mixer here. The keyboard sends a gate signal to the envelope generator, which modulates both the mixer and the filter. So let's see that in action. First, I'm going to reorder these. Going to disconnect a couple of things. I'm going to take the output of the mix and connect that to the voltage controlled filter. Next, I need to have a second VCO, so I'm going to right click on that and I'm going to go to duplicate. Also have that connected to volts per octave, and then I'm going to use sawtooth wave from both of those in order to create something a little bit more interesting. Now I'm going to drop this down by right-clicking on it and telling it that I want the initial frequency to be set to 258 hertz. Let's say that. So it's going to be slightly detuned. Next, I need to have the gate signal going in to the ADSR, and that is going to control the level, but it's also going to control the filter, which is good. Then we're going to take the low pass and send that to the output. So we should have a cool lead type sound now. Okay, it needs a little envelope shaping. Nothing I can't do with a little bit of release. And I think I'm going to get rid of one of those and connect a delay with just a little bit. Let's go 0.2 on the dot. Which now you can hear in glorious, glorious stereo. I could also play that with the mix, in which case we get a little bit more of the feedback in there. That just lets me fatten the sound a little bit. I find it be kind of useful. I could also play around by sending the pre-filtered saw into there and then connecting that to the output, to the VCA mix, and then I could take that, connect that directly to the mix as well from the output of the low-pass filter. And then if I adjust my time, we get some interesting effects. And let's take that down even further. But it produces a nice kind of fast, plucky lead type sound. After that, let's look at the pad. So the pad is going to increase things in complexity. We're going to use a pulse width modulation wave that's modulated by an LFO to create sweeping harmonics. The keyboard is going to send volts per octave to the oscillator and a gate to the envelope generator, which controls the volume of the mixer and can modulate a filter. To make the pad more pad-like, we're going to send the mixer to a reverb unit that is modulated by the LFO and then back to the mixer. So finally, for pads, the key is to use long envelope and attack and release times, so we're going to set those accordingly as well. I'll start by setting a long attack and a long release. Then I'm going to start making some changes. We're going to delete that VCO, and we're going to change the output to square. Next, we don't need delay anymore, but we do, in fact, need some reverb. So let's get a reverb. I'm just going to clear all of my filters, and then I'm going to go to favorites, and we're going to go to reverb. And I think that the spring verb will serve its purpose well. So we're going to take the output of channel 1 to the input there, and then we're going to take the wet and send that to channel 2. Okay, now we need an LFO, or low frequency oscillator. So I'm going to clear my filters again. Select just the VCV objects, and we're going to get the LFO. All right, this LFO is going to do double duty in that it will be sending a low frequency wave to control both the pulse width modulation, and it's also going to control the reverb. So I'm going to take that, I'm going to say, put that up into there. We'll take it down on the frequency, make it nice and slow. Then I need to have it also control the dry-wet balance on this. Or I could have it control the amount of the level. Let's try the level first. You can see it pulsing in sync with that. That's always a cool thing. Then I have my VCF hooked up, and that is being controlled by the ADSR envelope, and that is also controlling the VCA mix, the actual mix. So let's hear what this sounds like, and then we can make some adjustments to it. That still is a little too fast, I think, on the attack. We're going to make that considerably longer. And I'm not getting as much reverb as I would like, so let's add a little high-pass filtering, and let's have that control the mix instead. Okay, now let's dial in the amount of pulse width modulation that we want. Take the volume down so I'm not blowing anything up. Okay, that sounds pretty cool. I'm digging this. I have increased the amount of resonance on the VCF. I'm still using a low pass, but I could easily change that over to a high pass, and we'd hear something very, very different. So here, I'm going to change the direction of the cutoff frequency CV. I'm going to invert it to roughly the same place. So what I've done here by inverting it is I've taken the signal that is going in from the envelope, and I've basically said flip it around. So if it goes up, instead go down by that same amount. So it's taking the cutoff frequency, and instead of sweeping it upward, it's sweeping it downward, which can be a really, really cool effect. But I'm going to go back to the low pass filter, and we're just going to stick with that for now. Yeah, cool. Next, let's take a look at how you can use the noise module to create percussive sounds. So in a PERC patch, a keyboard is sending a gate signal to an envelope generator, which is modulating both a filter and a mixer. But here, there is no volts per octave connection from the keyboard to an oscillator because we're just going to use a noise generator, which by its very nature is just constantly outputting noise and has no need for a volts per octave connection. You can, however, send the volts per octave from the keyboard into the filter frequency, though. And you can also replace the keyboard with a sequencer if you want to create something really interesting. Let's take a look. So I'm going to disconnect my oscillator completely and the reverb. Okay, we'll move that out of the way, and we need a noise. So I've still got my MIDI-CV connecting to the ADSR, but here I'm going to drop things down considerably. I'm going to sustain, and our release time is going to be super short, just to start with. We'll play around with that, though. Now I'm going to send noise into a filter, and the filter is going to go into my VCA mix. We'll start with white noise, and we'll start with a low pass, and then we'll go from there. Okay, so very basic. Let's give it a shot after I connect the cutoff to the VCF from the ADSR. Okay, that's a little much. Let's increase the decay time and the release time. All right, that's starting to get better. I'm going to connect retrigger there, and let's hear that. All right, my release time's a little hot, so we'll take that down. And I can adjust the cutoff frequency. And okay, that sounds like it's starting to sound like a decent type of snare object. But there's only one problem, which is that I can't play a lot of these. So I'm going to connect it up to a sequencer. I'm going to randomize the sequencer. I'm going to take the output of the sequencer in terms of the different steps, and we're going to use that. So let's connect that to the gate. And let's try that. We can change the noise, and that might give us some different options. Okay. That's kind of cool. I could make this more interesting, though, by adding in a VCO, which I've already got, but I'm going to copy the VCF. And here, by using that sequencer, I've created a really, really basic patch that's allowing us to get some cool sounds from just a sine wave and a little bit of violet noise in this case to create just kind of a really basic drum pattern. If I wanted to have a little bit more fun, I could also send one of these over to the input of the spring verb, and then we could take a listen to that. So again, that just gives us some more options. It's kind of fun to play around with these and see what you can do and create different types of basic percussion patterns using the sequencer or using the keyboard. On the subject of using the sequencer, let's talk a little bit about the sequencer itself. So in the sequencer, we're going to need to use a master clock, which will be very, very useful. That's going to send a signal to a sequencer and to a clock divider that controls a second sequencer. The first sequencer here is going to control an oscillator and an envelope generator with a volts per octave and gate, respectively. Sequencer 2 is only going to send gate signals to an envelope generator. Now, what's going to happen there is that the oscillator and a noise generator both send audio to a mixer, and each channel on the mixer is controlled by the output of one of the envelope generators before passing through to a filter and then to the speakers. So this is going to be very similar to where we're at now, but just a little bit different. So first, let's create a second sequencer, then a second envelope generator. I'll move that over here. And now we need a clock and a clock divider. But first I'm going to disconnect cables. We're going to move the spring verb and the delay down, and the VCF and the noise, all that. Let's get a clock. First I'll reset tags. Clock generator. Here we go. Oh, there are so many. In fact, I'm just going to use a really, really basic one over here. This is just a BPM, and it outputs CV or gate. Then I need a clock modulator. So I'm looking for a clock divider, and I can search with divide. And we can find that there are a bunch of different ones still. Which one do I want? How about... We'll just go with this particular clock divider, because it's pretty easy. Okay, so I'm going to take the gate from the clock and connect it to the clock divider. Then I'm going to disconnect my sequencer, move my LFO there, move my ADSR there. So my first sequencer is going to take the signal directly from the clock. So I'm going to grab that and sync it to the clock. And now you can see that the clock button is synced directly like that. I'm going to randomize this sequencer so that we've got different patterns. I'm going to take a signal from the clock divider, and we're going to send that to the clock here. So this clock is now going to run half as fast as the initial clock. Okay, then I need the ADSRs, and I need them to control different sources. So the first source is going to be sending pitch, CV, and gate triggers. So we're going to send the pitch to our volts per octave in the VCO. I can delete the LFO for now. Then I'm going to just reset that. And then I'm going to send the output that triggers to here in the first. Now remember that this does not have a sustain, so that is something to be aware of. From the second one, it's going to go just to control the envelope for the noise, so I'm just going to send out the trigger to here, and then we're going to control the trigger with CV in both cases. And then we're going to send everything to a filter, so I need a VCF and only one VCF. My noise needs to go into channel 2. My sine wave needs to go into there, and then I'm going to swap those modules around. Take the input of mix, and then I'm going to take my low pass outputs and control those. Okay, so I can see I'm getting some sound out of here, but it's not really going anywhere. What is it not doing? Let's take that all the way up. There we go. Let me try one of these different CV patterns. Okay. Now I can also adjust the speed, and we can make this a lot faster. Let's double that tempo. I can adjust the notes that are played with the trigger buttons down here on the sequencer. Or I could even send this to the FM modulation. And of course I can send things into other sources. So it's getting more complicated. I've got a lot of cables kind of messing up around the view, but I'm creating just some really cool stuff with the sequencers. I've got one sequencer that's just modulating the frequency of the VCO and changing the pitch. I can switch that between the 3 different rows, row 1, 2, 3. I can set which notes are played with the trigger buttons. The other one is just sending the trigger pulses out to control the percussive hits from the noise generator. And then everything's going to the filter, but I can also send it to the spring verb or to the delay to get other interesting sounds. So this is a really, really cool thing that you can do in order to create sounds. You can just play around with the sequencers and then maybe create another patch that's going into mix channel 3 or mix channel 4 where you're doing something that you play with the keyboard itself. But let's move on. Why is this important? Well, because it's a great practical example of how you route audio and control signals among various modules to get a desired result, similar to using a patch bay and all sorts of outboard gear in a recording studio. It's very, very similar also to how signals are bused to aux tracks and effects chains in a DAW. And understanding routing and signal flow is a key concept, not just for mixing and mastering, but for advanced applications in audio like Maxim SP or Super Collider programming, especially in ambisonic audio, and if you're going to use audio middleware engines for video game sound design. But that's it. I hope you've enjoyed this, and I'm just going to let the computer play us out.